In this video, we compare the drag of a conventional windsurfing board with the drag of a board with a curved transverse step in a virtual towing tank simulation. We'll use old RRD 149L board as a prototype. We'll be considering drifting motion at a constant speed of 36 km per hour. The simulation model is fairly simple. A free surface is completely flat, that is, no chop, no waves, and no dynamic loads from the sail force. Clearly, this isn't entirely accurate. Printed in blue font, the trim angle, the drift angle and the stern's immersion are not constant in real conditions. In our coordinate system, the flow is directed along the x-axis, and the 0 point of the y-axis coincides with the undisturbed free surface level. The goal of the simulation is to determine required trim angle, drift angle, and stern sinkage at given speed to achieve the specified values, already marked on the white background: a lift force of 1064 newtons equivalent to 108.5 kilograms of supported weight, and a drift resistance force of 367 newtons. The center of pressure is also specified to be located approximately 66 centimeters from the stern. We take a 42 centimeters fin, composed of a symmetrical NaCa 9% profile, positioned absolutely vertically, meaning the board is not railed and has no heel angle. We also assume fin to be completely rigid, meaning it will not deform under the influence of forces. There's no twist, no fin flex. As a prototype, a board 235 centimeters long and 73 centimeters wide was roughly prepared in the CAD subsystem. It was specified that the rocker section up to 80 centimeters would be completely flat. Then there's a rise toward the nose up to 23 centimeters. The dead rise is taken equal to 0. We first build a grid based on rectangular cells and refine it along the free surface. Along the end, specifically refine the part of the free surface that subsequently interacts with the board's hull, forming a forward flow and a braking line. Additional refinement was applied to the leading edge, the trailing edge of the fin as a wing, and the area where it meets the board. The fin wake was also slightly refined. This meticulous subdivision was done to keep the cell count low, 2.5 millions, to reduce calculation time. After running the solvers and some operators' involvement in adjusting the parameters, the approximate trim angle is found to be 3.2 degrees, the drift angle is 2.9 degrees, and the stern immersion is 34 millimeters. Validation and verification of the solution are difficult. We will judge based on indirect data. For example, we get the following picture of a wake behind the board and two crests extending from the sides of the board. The board is moving on a port tack. A small fin wake is also visible. This image shows the water-air fraction generated by the solvers. At this point, flow backup occurs because our bottom is flat. A thin stream strikes forward, then some semi-streams of droplets with a mixed fraction form, disturbing the free surface from the front. Such picture is produced by CFD. And if you look at the velocity vector data in one of the cross sections, you'll see that CFD shows swirls of airflow on the part of the board before the flow separation line. This is also evidenced by the complex streamlines. These are air streamlines that run slightly above the free surface. Next, we'll derive the excess pressure coefficient along the bottom of the board running at calculated trim angle of 3.2 degrees. This shows that there's a flow stagnation line, and most of the lift is generated in the front section near the foot straps, given that our bottom is longitudinally flat. The influence of the fin, which operates as a vertical wing, is also visible. Such pressure distribution creates a moment relative to the x-axis of approximately 12 Newton-meters, which is directed in the opposite direction from that created by the fin. If we calculate the excess pressure coefficient for the cross-sections along the board axis, which is slightly rotated relative to the x-axis at trim and drift angles, then we obtain the following pressure distribution. The board's drag force is quite high. The board's planing efficiency is approximately 9 units. Friction force due to viscosity is significant all over wetted surface which has rather small aspect ratio around 1. We'll also calculate the excess pressure coefficient separately for the fin. This is the windward side. The obtained required drift angle is approximately 2.9 degrees. The center of pressure is located around 18 centimeters from the line of contact with the board. We can also calculate the excess pressure coefficient for the fin at different depths based on the fin cross sections. It's clear that many sections operate quite efficiently with a noticeable pressure difference. Except for the lowest one, where pressure equalization occurs due to flow transfer. The fin hydrodynamic efficiency is rather high 13.8, while the board efficiency is only 9. Finally, the total drag is about 145 newtons. Let's try to reduce this value for given lift and side force in part 2 using a transverse cambered step to rise the board planing efficiency. Part 2. Analysis of a board with a modified bottom. Objective and setup. This section investigates the planing performance of a board fitted with a modified bottom, under the same idealized conditions as Part 1, a perfectly flat water surface and a constant flow speed of 36 per hour along the x-axis. The goal remains to achieve nearly identical values for lift, drift resistance, and center of pressure. The key modification is the introduction of a step on the bottom, shaped as a curved wedge that can be easily applied with putty. It is important to note that a standard wedge could also be used. The optimal location and height of the step were predetermined using discrete vortex methods. The planing behavior of the resulting wetted area, which now has a higher aspect ratio greater than 2, closely resembles the flow around a thin wing. Computational model. To accurately capture the ventilation effects in the cavity behind the step, the computational mesh was significantly refined in that region. This resulted in a higher resolution model comprising approximately 3.5 million cells. Results and operational parameters. Through solver calculations and parameter adjustments, the required operating conditions were determined. To generate the target forces, the board now operates at a significantly reduced trim angle of 1.5 degrees, with a drift angle of 4 degrees and a stern immersion of only 14 mm. Flow analysis. Phase fraction water-air. The distribution of water and air shows that the small trim angle and zero dead rise cause the jet spray to be directed forward, with a visible mixture of both phases. The results confirm that effective ventilation is achieved in the cavity behind the step. Skin friction coefficient distribution also confirms good ventilation here. Velocity field. The velocity profile on a central XY cross-section reveals a zone of airflow deceleration ahead of the step, accompanied by complex, time-dependent eddies. Air streamlines. Streamlines originating just beneath the step show a highly complex flow pattern, featuring sharp turns and vortices that form and dissipate. Water streamlines. The water streamlines, visualized below the free surface, present a flow structure similar to that around a thin wing. Pressure distribution. The coefficient of excess pressure distribution along the bottom indicates that the wetted planing patch has a favorable aspect ratio. The pressure diagram is well filled over a relatively short distance of about 27 centimeters. Performance evaluation. Board efficiency. The modified design allows the target lift to be achieved at the low trim angle of 1.5 degrees, resulting in relatively low drag. This yields a high hydrodynamic efficiency of approximately 14 for the board itself. Fin performance. The CFD results indicate that a higher drift angle of 4 degrees is now required from the fin. This increased angle of attack leads to higher fin drag, reducing its efficiency from 13.8 to 12.1. The center of pressure on the fin has also shifted lower. This is a direct result of the free surface interfering with the fin's upper section, which fails to function as a normal airfoil and generates no lift. Only the middle and lower sections operate effectively. Conclusion. The final configuration for the stepped board resulted in a trim angle of 1.5 degrees and a drift angle of 4 degrees. Crucially, the total drag of the board and fin system was reduced to 107 newtons, a substantial improvement over the 145 newtons recorded for the conventional board in Part 1. This suggests that under near-ideal, flat water conditions, this modified system requires less thrust, the forward component of sail force. This could be advantageous in light winds, potentially allowing the board to remain on a plane for longer periods. Questions regarding stability and performance in choppy water were beyond the scope of the simulation and will be addressed during practical on-water testing, is to be covered in Part 3.